Hello everyone. So I welcome you again in this lecture, and in this we are going to talk about the deletion operation in the AVL trees. So far we have discussed what is AVL trees. It's a self-balancing trees that make sure that the tree always remain balanced, and the balancing we are checking with the help of the balancing factor. Already we discussed the insertion operation. In the insertion we have four cases. If you compare the insertion with the deletion is comparatively little complex. But again, it's interesting to see that how the things are managed, how the tree maintains the self-balancing structure. Okay, so it starts here. Already we have discussed that ABL tree is a binary search tree. So when we delete any node from the binary search tree, it will be same way deleted like we have already discussed deletion in the binary search tree. So just to remind you that in the BS tree we have three cases possible. You may want to delete a node which is a leaf, or a node may have one child either left and right, or the node may be having two childs. So we have three possibilities. So all the cases that we have discussed, the deletion in the binary search tree will again applicable here. So whenever any node to be deleted, we will be deleting in the same way like in the binary search tree, but because of this deletion it will disturb the balancing factor. Means the balancing factor of each node may not be maintained as balanced, means the value will not be remain as plus 1, minus 1 and 0. Plus 1, minus 1 and 0 we are assuming as a balanced value, and whenever any node does not maintain these value out of these three, then it is said to be unbalanced and we need to perform some operation. So whenever we delete a node, because of this deletion the tree may getting unbalanced, and then we need to rebalance it to maintain the AVLness property within the tree. Now whenever the tree getting unbalanced, we need to perform some operation, and these operations are done in the form of rotations. So when we talk about deletion operation, we are doing two type of rotations. We are calling as left rotation and right rotation. Now left rotation, or you can call it L rotation, and right R rotation. L rotation and R rotation are basically the mirror image of each other. So whatever we are doing in L rotation, we are doing almost in the opposite way in R rotation. So first let us understand that how the rotations can be applied before we move to any example. So let us consider that A is a critical node. Already we have discussed the critical node. The critical node is a node whose balancing factor get disturbed. Okay, and we need to fix this. And B is the root node of its left subtree. So A is the critical node, and B is the root node of the left subtree. So once you find the critical node is having the child, may have child the left side and the right left child and the right child. So for the left child, B is the root node of its left subtree. If node X present in the right subtree of A is to be deleted, then there can be three different situations. Now let us assume that the node which we are interested to delete will be existing in the right subtree. So here when we talk about the deletion, and the deletion is existing in the right subtree, we are actually talking about the R rotation. And here we have three different situations. So let us understand what are these three different situations. So overall you can say that for R rotations we are having three situations. Similarly for L rotations we have three situations. So that makes six possibilities in the deletion. In the insertion we have four possible cases. Here we have six possible cases. So we'll understand carefully and in detail one rotation, R rotation first, and then we can directly move to L rotation, because L rotations is actually the opposite behavior of the R rotation. Okay, So very first is R0 rotation. Node B has a balancing factor 0. What does that mean? It means if the node B has 0 balancing factor, now keep in mind, let us uh, revise that A is your critical node and B is the root node of the left child of the left subtree, and we are deleting a node which are occurring in the right subtree. This is the scenario. Okay, so here this B is having a 0 balancing factor. Now based on the balancing factor we are having the case. So here your node which you are going to delete is existing in the right subtree, and the balancing factor of the left subtree root node is 0. This is how we are defining that this name R0. Okay, so if the node B has a 0 balancing factor, okay, and the balancing factor of node A disturbed upon deleting the node X, and this is our critical node A, which is need to be fixed because when we delete a node, this node is not maintaining the balancing factor to +1, -1 or 0. Then the tree will be unbalanced, and we need to get it balanced by doing this R0 operation. Now understand this. Here we are having this is a height height h, and this also height h. So if you do the difference of this, so this is actually, you can just this is a kind of tree. This is a tree. T1 is a tree which is not shown here, but instead of showing the entire tree, we are showing with the one box. So this is the height, that means h, and this is 1 and 2. This means this is h plus 2, right? So means if you look at the height of here is h plus 2 here, and if you look to this side, this is h and 1, so this is h plus 1. Okay, and here we are doing left minus right. So when you do h plus 2 minus h plus 1, what you get? You get 1. So this is 1 here. So here we are doing the balancing factor equals to left height minus right height. So here you can see that when you delete any node from here in the right subtree, and because of this the height of this tree is going to reduce by 1. So now this is h minus 1. Now because this becomes h minus 1, so what is the impact of this? Let us find the impact of balancing factor after the deletion. So we have to do left minus right. So if you look at the height of this is h, then h plus 1, h plus 2, this side we have h plus 2, and this side we have h minus 1 and plus 1. So h minus 1 plus 1 is h. So when you do this minus, so h plus 2 minus h is 2. So here you can see this is 2 here, and because this is 2, that means this is not balanced now, and we need to do some rotations. So what is required? Performing the R0 rotation. So we have to perform the R0 rotation. So what actually this is scenario, this is similar to the LL case. So in the LL case, what is required? You need to rotate from here the right rotation at A. So when you do the right rotation at A, what you will get? You will get that this goes up, this goes up, this goes down, this becomes the right child of this, and this becomes the left child of A. So you can see here. Okay, and now if you find the height, this is, if you look at this side, this is h and one edge, so h plus 1, and when you look here, this is h plus 2. So we will find the balancing factor as h plus 1 minus, and when you minus this value, this will minus h minus 2. This is what? This is minus 1, which is balanced. So this is how we can fix our tree, and now this is balanced. So we need to keep in mind that R0 is actually done as a LL case. Right rotation at the critical node. Okay, moving to the next. Okay, let us take the example of R0 case of deletion. This is actually LL case. So you can memorize R0. We need to do this kind of rotation. which we are doing in LL case. So here you can see that this is the tree given to us, and here this is AVL tree because the balancing factor uh, is actually 1 0 minus 1, so every node is balanced here. But when we want to delete 30, so this is just a leaf. As a rule of binary search tree, the leaf can be deleted directly, so you can delete this node, but because of this deletion it will impact on the balancing factor. So here you can see this is actually 2, and 2 minus 0, because this is there is no right subtree, so this is 2, so this becomes your critical node. Now we have discussed that, let us say that this is your critical node is A, and the left subtree root node is B, and we are deleting from the right subtree, so we are deleting the node which is actually a part of the right subtree. So this is the example of R0, because you are deleting from the right subtree. So when I say 0, 0 is basically refers to the balancing factor of the left subtree root, and R is the node which existing on the right subtree. So in this case, what is required? This is very similar to the LL case, and in the LL case we need to rotate from the critical node that we are calling as Z in the previous uh, discussion when we discussed about insertion. So you need to rotate from here, and as a result of this rotation you can see that now tree is going to be balanced, and because here the balancing factor will be in the range of 1. Okay, so let us move to the next part. Now R1 rotation. Now as the name suggests, this 1 is basically referring to the balancing factor of the B node, and R means we are deleting a node from the right subtree. So R1 rotation to be performed if the balancing factor of the node B is 1. In R1 rotation, the critical node A is moved to its rights, having the subtree T2 and T3 at its left and right child respectively. T1 to be placed as the left subtree of the node B. Okay, so let us understand what is written here. This is your AVL tree, and here you can see that this is balanced. So here you can see this is, if I want to find out the height of this, so height of this you can find out by reaching from this node to the leaf. So this is now this tree is having h minus 1 height, this tree is having h height, so definitely the height of this node is find out by this one, because we always find the maximum uh, number of edges or the maximum path from the root to the leaf. So the height for this node will be h plus 2, and here you can find this is h and plus 1, so h plus 1. So that means if I find the balancing factor, you will do L minus R, this is h plus 2 minus this, so minus h minus 1, which is plus 1. So here you can see this is 1, so this is balanced here. Now the case is deleting a node from the right subtree of A. So here we want to delete something from the right subtree of this node, and because of the deletion the height of this is going to reduce by 1, so this becomes h minus 1 because of this deletion. Now we'll see the impact of this will remain h plus 2, and this becomes h minus 1 and plus 1, this is h. So when you subtract h plus 2 minus h, you get 2. That means this is becomes unbalanced, and in our case this is a critical node, and this is your root of the left subtree, this is B, and this is the deletion node which is in the right subtree, and the BF value, the balancing factor value of this node is 1, so we are in this case. So when this is having a 1 value, we are again doing this kind of LL case. So what is required here? You need to move from here, or what you will observe here, if you want to do the direct rotation, what you will see that B is going to become a root node, and you simply uh, stick this part to this as a left subtree, and this becomes the right child of B. So you can see here that B becomes the root, and this becomes the right child of B, and this becomes the left of A, and our tree is now balanced. And you can have a note here also, this becomes, this is h minus 1, T2, this is h minus 1, this is h, but if you compute, so this is actually h and h plus 1, and when you find out from here, so this is h minus 1 plus 2, so this is what, h plus 1, and h plus 1 minus h plus 1 will be 0, and this is, and this makes your tree balanced. Again we are doing almost the LL case here, so just keep in mind when you are doing R0 rotation, again we have moved from here. In the R1 scenario also we did LL case. Now let us take an example of R1. So this is our AVL tree, because the roots are because the nodes are fulfilling this property that the left is having less than the root, right is having more than the root, and also the balancing factor at each node is uh, maintaining the one value, maximum one value. So now we want to delete from the right subtree, because we are discussing the R rotations. We have two rotations possible in deletion, R rotations and L rotations. So we are talking about the R rotations. In the R rotations, we are deleting the node from the right subtree. So here we are interested to delete this 55. So the moment when you delete this, and after deletion, we have to check that what is the impact of the deletion on the balancing factor of each node. So we will realize this, that this becomes 2 here. So this becomes a critical node, and the left child will form the B. So this is A, and this we are calling as a B, and then from we delete it from the right subtree. And if you notice here, in the previous case, in the very first case, the value of B, when I say value of B, means the balancing factor of this node is 0. So that is called R0 case. Then we have 1 here, so this is called R1 case, and R1 case will be dealt similarly as LL case. So in this case, what is required, you need to make a right rotation. So whenever you make a right rotation, simply what is required, this becomes the root node, this becomes the right child of 40, and this goes and stick to here, and this becomes the left child of 50. So you can see here we have performed these operations, and as a result this tree becomes balanced. So this is AVL tree. Because of the deletion, it becomes non-AVL tree, and then we do the some rotations, and that again becomes the AVL tree. So R1 rotated tree will make that resulting tree as a AVL tree, which is a balanced tree. Okay, then we have a third case, R minus 1 rotation. Just to remind you that we have R rotation and L rotations, and each rotation will have three different cases. So this is the last case of R rotation. So here again, this minus 1 refers to the balancing factor at the node B, and we are deleting a node from the right subtree. So R minus 1 rotation means when the balancing factor is having minus 1 value. So we have three possible values, either you have 0 value or we have 1 value. We discussed about 0 case, we discussed about 1 case, and the third case possibility is minus 1. This is what we are discussing now. This case is treated in the same way as LR rotation. So here, whenever you find this case, we will be doing LR rotation kind of activity that we have already discussed while insertion. So what is going to be observed here? The node C, which is the right child of node B, becomes the root node of tree with B and A as its left and right child respectively. So whatever is written here, we can see here, and we will see that how to apply or implement this R minus 1 rotation case. So R minus 1 is very similar to LR case. In the LR case, we need to do the left rotation and then the right rotation. Left rotation we are doing at the immediate parent, and R rotation we are doing at the critical node. This is the same that we have discussed in the insertion. So this is your tree, and you can see here this is the height status is given, and if you want to find the height of this, so this is h minus 1 and 2, so this becomes h plus 1, and this is h, and this h plus 1. But to keep in mind, when I say this is h plus 1, this is actually not completely correct, because height is find out by finding the maximum edges or the maximum path possible. So the maximum path is actually this one, not this one. So this is h minus 1, and when you add h minus 1 plus 3, so this becomes h plus 2. So an h plus 2 minus, so I will find balancing factor as h plus 2 minus h minus 1, which will give you plus 1. So here you can see 1, this is AVL, because the balancing factor is having a difference maximum 1. Now here you can see when you delete any node, so because of the deletion here, this impact the reduce of the height, so this become h minus 1. Because of this h minus 1, the resultant is this will be h plus 2, and this will become h minus 1 plus 1, this is h. So when you difference these two, it results into 2. So whenever the balancing factor is more than 1, it will become unbalanced. So what is required, you are going to do the LR case, you are into the LR case. So one thing is, either you can do the LR case, or if you are comfortable in doing directly, what is observed here, you can see here, you need to look here, this is going to become this part, C part. Okay, this is going to become, means whatever the right child of B. So when we are doing this kind of rotations, our main focus is to find out the A is the critical node, and the left subtree root is B. So when you find that B is minus 1, you look to the right child, and we are calling it as a C. Now this C will go to the root position, this C will go to the root position, and A will become the right child of C. This is something to be done, and the right child of C becomes the left child of A, and the left child of C becomes the right child of B. So again I repeat, either you can do the LR case, do the two rotations separately, or if you are comfortable, you can do directly. What is required, this will become the root, and this root becomes the right child of this, and this right child becomes the left child of A, and the left child becomes the right child of B. So you can see here, when you do rotations, the left child T2H minus 1 become the right child of this B, and the right child of C T3 become the left child of A, and this becomes the right child of C. So though it looks like means maybe confusing, but I'm very sure when you do on the paper, when you look to any numerical, you will be easily able to do this kind of uh, change in the structure. Okay, so let us take one example that how the things will work. This is the example of r minus 1 case. So this is our AVL tree, because the balancing factor is at most 1, means the maximum value of the balancing factor is 1. So when you delete node 60, this is node 60, we will delete as per the rule of the BST. It's a leaf, so we'll delete this node. But the impact of this deletion is that it will leave this as a 2 here. Now this is the critical node, and then you have to look to the left subtree. This is minus 1, so that means you are, and you are deleting from the right subtree, that means you are in the r minus 1 case. So when you are in the r minus 1 case, you have to look to the right child of this B, and we are calling it as a C. Okay, so when you call this a C, what will happen, because we don't have any subtree existing here, and we have seen that this becomes the root, and this becomes the left child of this. So simply here we don't have any extended tree, so we don't need to do anything. Otherwise the left child of this becomes the right child of this, and the right child of this becomes the left child of this. But because we don't have anything here, you simply make this as a root, and this becomes the left child. This is one thing is required. This is one way of doing. Or what you can do, this you can take it as a LR case, and in the LR case, what is required, you need to move the left rotation at here. So when you do the left rotation as here, what you will get something like this: 50, 45, and 40. This will go down, this will go up, and then you have to do the right rotation at here. So what is the impact of this when you do this? So 45 becomes the root. This will be here and this will be here. So this is what you get. So either you can do LR, or directly you can use uh, the properties as we have discussed, and you will get the final structure. So here you can see that now this is balanced. So to summarize, so deletion will be done as per the binary search tree rule, and when we do deletion, it will impact on the balancing factor, which may be disturbed, which may be unbalanced, and then you need to do rotations. Rotations are two types: L rotation and R rotation. R rotation we have discussed. Each rotation have three cases. So when you have R0 rotation, R1, R minus 1, so this is equivalent to LL case and LR case. This you can memorize. Similarly, we have three cases in the L rotations. We have L0, L1 and L minus 1. Now, how the name is given, just keep in mind when I say R rotation means the deletion is happening in right subtree of critical node. If the deletion is happening, or the node which is deleted is existing in the right subtree of the critical node, then this is the R rotation cases. So in this case, we are calling the A as a critical node, and the left subtree root is called as B, and you have deleted from here. This is the R case. In the left rotation, what is happening? We have, this is a critical node, and we have deleted from here, and this right side, the right subtree root node, we are calling as a B. So based on the value of this, we call the case. So if the value of this B is 0, means if the balancing factor is 0, this becomes the R0 case. If it is 1, it becomes R1 case. If it is minus 1, it becomes R minus 1 case. So we will take some examples to understand in a better way. So in the next part, we will take some numericals. We will do some insertion and deletion, and we will realize that how the rotation is done to make our AVL tree balanced. So this is all for this lecture. We will take some examples in the next video. Thank you very much.